You know, every single piece of modern technology you use, from the smartphone right there in your pocket to the car you drive, all the way to the James Webb Space Telescope peering into the very dawn of time, it all runs on one silent, unsung hero, the semiconductor.
So, that begs the question, right? What exactly is a semiconductor? And how did this amazing material, which literally starts its life as simple sand, end up completely changing human history more than almost any other invention out there?
Okay, let's get into it. Here's how we're going to break this down. First, we'll look at what makes this material so special. Then, we'll see how it becomes a tiny, microscopic switch. After that, we'll learn how billions of those switches speak the language of computers, explore the wild process of actually making them, and finally, really get a grip on their impact on our world.
All right, first things first, we have to understand what makes a semiconductor so fundamentally special. And honestly, the clue is right there in the name.
To really get what a semiconductor is, it helps to look at the two extremes. So on one end, you've got conductors, like a copper wire. Electricity flows right through them, no problem. They're basically always on. On the other end, you have insulators like rubber. They block electricity completely. They're always off.
And this, right here, is the semiconductor's superpower. It isn't stuck being either on or off. A material like silicon sits right in the middle, and its absolute genius is that we can precisely control its ability to conduct electricity. We can switch it on and off whenever we want.
So how do we get that control? Well, the secret sauce is a process called doping. It sounds weird, but it's where scientists intentionally add tiny, super precise amounts of other elements, impurities, into the otherwise pure material. This isn't a mistake. It's a totally deliberate tweak that gives it these amazing new powers. This doping process creates two different flavors of the material. If you add an impurity that brings along extra electrons, you get what's called N-type material. It's got a bunch of negative charges ready to move. But if you add an impurity that creates a shortage of electrons, you get P-type material, which has these little holes that act like positive charges. Okay, so we've got this really clever material. How in the world does that become the single most important electronic component ever invented?
Well, when you combine these N-type and P-type materials in a very specific way, you create something incredible, a transistor. It's an electronic switch, yeah, but the key difference is right there in that quote, without any moving parts. This was a massive leap forward, no wear and tear, and it can flip on and off billions of times a second without ever breaking down. And that simple, ridiculously fast on or off state. That's it. That's the physical reality behind the binary code that our entire digital world is built on. Every single one is just a transistor turned on, and every zero is a transistor turned off. That's the language of computers, spoken by these tiny switches.
But it gets even better. A transistor isn't just a switch, it's also an amplifier. A tiny, tiny trickle of electricity can be used to control a much, much larger flow. That's the magic that lets a small chip in your phone power that big, bright display. It's all about leverage.
Okay, I get it. It's a switch. But how do you go from a simple on-off switch to something that can play a video or run artificial intelligence? How do these billions of switches actually learn to, think?
The answer is by combining transistors into something called a logic gate. Think of a logic gate as a tiny decision maker. It looks at one or more inputs, just ones and zeros, and then it spits out a single answer based on a very simple rule. So for example, take the AND gate. It's really strict. It will only output a 1, a yes, if the first input and the second input are both 1. If either one of them is a 0, the answer is 0. No exceptions. Now the OR gate is a lot more relaxed. It'll output a 1 if the first input or the second input is a 1. It doesn't care if both are. The only way you can get a 0 out of an OR gate is if you give it 2 zeros to start with.
Now on their own, these gates are really simple. But here's where the magic happens. When you start connecting millions or even billions of them together in really clever ways, you can perform any calculation or logical task you can imagine. Every single thing your computer does is just the result of these simple yes or no decisions happening at an unbelievable speed.
So we know what they do, but how are these impossibly tiny, complex circuits actually built? Well, get ready, because this is hands down one of the most precise and complex manufacturing processes humanity has ever created.
And you're not going to believe it, but it all starts with sand.
Yep, plain old sand, which is rich in silicon dioxide. This stuff gets melted down and purified to an insane degree. We're talking 99.9999% pure. Then it's slowly grown into these perfect single crystal cylinders called ingots.
Those perfect crystals are then sliced into these ultra-thin discs called wafers. And that's when a mind-blowing process called photolithography kicks in. The easiest way to think about it is like super high-tech stenciling, but with light. You coat the wafer, shine UV light through a mask that has the circuit pattern, and then etch that pattern permanently into the silicon. And the craziest part? They repeat this whole cycle dozens of times to build up the complex 3D layers of a modern chip.
And the scale we're talking about here is it's almost impossible to wrap your head around. The tiny little features being carved into these chips are measured in nanometers. That's a scale more than 10,000 times smaller than the width of a single human hair. It's just incredible.
Okay, so let's zoom all the way out. We've gone from the nanoscale to the global scale. Let's talk about why this amazing technology underpins literally everything in our modern lives.
Just think about our world for a second. Smartphones, the internet itself, artificial intelligence, modern cars, life-saving medical gear, satellites, the entire global financial system. Literally none of it would be possible without the semiconductor. It just wouldn't exist.
They are the invisible bedrock of modern life. We don't see them, we rarely think about them, but from the tiniest switch to the entire global economy, they form the absolute foundation of our digital civilization.
So think about that. From a simple grain of sand to a globe-spanning digital network, the semiconductor is the ultimate proof that mastering the smallest things can have the absolute biggest impact. And it really makes you wonder, if this is what we built by learning how to control electrons in silicon, what are we going to build with the next world-changing material we discover?